Hello everyone. So today we're working with a homogeneous first order equation here. So we're gonna solve for y, where dy dx equals x squared y squared plus x to the fourth over x cubed y. So how do we know it's a homogeneous first order equation? So when you're given a first order equation dy dx equals f of x y, it's homogeneous if this happens right here. So if you take f of tx comma ty, it's equal to t raised to a power of n f of xy. So in other words, if you replace x and y with tx and ty, and t here is a constant, by the way, and if your result after maybe some simplification is that you have that constant t raised to some power times the original f of xy, so the other side of the dy dx essentially, then it's homogeneous. The other way to see if it's a homogeneous equation is that if your equation f of xy can be written as a function of y over x. So basically, y over x appears in several instances here. Okay, so if that is the case, what you're going to use is you're going to use a substitution. Use v equal y over x or vx equals y. That's what you're going to use to solve that equation. And more, we'll go more into that in 1 second. But let's go ahead and test it if it's homogeneous. So the first thing you do is you isolate the dy dx. In this case, the dy dx is already isolated for us. And you take whatever on the other side, and you're going to replace x and y with tx and ty, which we went ahead and did here. So we replaced the x with tx and squared it, the y with ty and squared it, and etc. And then what happened was that if you combine some like terms here, like t squared x squared times t squared y squared, that would make t to the fourth x squared y squared. And on the denominator, t cubed times t is a t to the fourth x cubed y. You can factor a t to the fourth out of both the numerator and denominator, which would cancel. And you have basically the original capital F of xy. Or what you have is t to the 0 times f of xy. So your exponent here that we're speaking about was 0, where we're talking about the n in the homogeneous, checking whether it's homogeneous. So it's talking about over here. Okay. So basically, you get the same function times some exponent of t here. So our equation is homogeneous. So once you check it's homogeneous, then you can go ahead and solve it. So by solving it here, we're going to let y equal vx. And what we're going to do is as follows. We're going to find what dy dx equals. Now dy dx you have to find using the product rule, and which we did. And we got to recall though that because originally v was equal to y over x, as was stated above, v is really a function of x here because y is a function of x. So if you have y equals vx, then if I want to take the derivative of that, you're going to use a product rule. So you would hold x and take the derivative of v, and you would get dv dx, plus then you hold v times the derivative of x, which is just 1 with respect to x. And what you do next is this. The original left-hand side, right-hand side, where you had capital F of xy, you're going to replace all the y's with vx or xv, whichever. And that's what we did here. And if you simplify it, so I always recommend you simplify, factor, what you can do to cancel. You get this expression right here. And therefore, this equation right here, and sorry, let me go back to what I had as my result, v squared plus 1. All of that would become this right here. So this is the side where we had dy dx, and this is the side where we have the result of replacing the right-hand side with y with vx, okay? So you have this equation now, and the point is with a homogeneous first-order equation is to get to this point, because at this point, this equation becomes a little easier to solve. How so? Well, I'm going to first of all subtract v on both sides, and if you did some algebra here, you wind up here, and this is a separable equation. And a homogeneous equation should always give you a separable equation at the end of the day here. And yeah, we're just going to go ahead and separate our variables and then integrate. So So v squared over 2 equals ln of x plus c. And yeah, our goal though is to solve for y. And as you recall, we let v equal y over x. Or if you prefer working with y equals vx, you're going to replace v with the y over x squared over 2 equals ln of x plus c. And this would come out to be y squared over 2x squared of x plus c. In other words, y squared equals 2x squared ln of absolute value of x plus c times x squared. So I multiplied both sides going from here to here by 2x squared. But when you get to this side and when you distribute and you multiply by the c here, 2 times c is just going to be another constant. So we can just leave it as c or a, whatever you want to call it here. Well, we'll just call it a, actually, just as a reminder that a equals 2c here. And that's about it. We can take a square root, of course, to solve for y explicitly. And technically speaking, you have like 2 solutions based on what the initial value is given here, if there was one, okay? But anyways, that's the general idea with a homogeneous equation. Is let me just go back here real quick to the beginning. Yeah, we test to see if it's a homogeneous equation by doing such. And what I always tell people also though is like if you can check whether you can simplify your equation first before going through these steps of checking whether it's a homogeneous, that'd be a good idea, because it sometimes makes things a little easier for you in terms of identifying the equation. If you possibly can solve it in terms of it's a if it's like a separable equation or first order. Here you can try both those things. Those won't work out here. So the next thing to try is some other method besides separable and first order, which would be homogeneous as we're doing, or like a Bernoulli or an exact, and it happens to be that it's a homogeneous, okay? And yeah, that would be it for that. All right, thank you for your time.